You know how to know for sure that you're a nerd? Well, you can tell for sure when it's 2 o'clock in the morning and you can't sleep because you're trying to figure out a better way to explain RC circuits and timing. So, guess what? I am the king of nerds because it's 2 a.m. and that's what I'm thinking about. RC circuits and timing. R and C, of course, is resistor and capacitor. And we know that T is equal to R times C. And that can be shown that the units of measure are seconds when R is in ohms and C is in farads, or R is in mega ohms and C is in microfarads. So for instance, let's say we have 10K resistor and a 470 microfarad capacitor. In that case, T equals 10K times 470 microfarad, or 4.7 seconds. It all seems rather simple, doesn't it? And it really is. But it's one of the most important concepts that you have to grasp in electronics. So let me draw you a little circuit here real quick. Here's our circuit. Our VCC is going to be 3 volts. And then we have a 1K potentiometer coming off of our supply. I'm only using 2 legs, the wiper and an outer leg. So we're using it basically as a variable resistor. It's coming to a 2200 microfarad capacitor, which goes to ground. And then in parallel, I have a push button switch so that we can discharge the capacitor. Here's the circuit, just like we talked about. There's our variable resistor, our capacitor running to ground, and our push button switch in parallel. So what we can do with this is we can use it to actually visualize the charging and the discharging of the capacitor. Now I'm going to power up the supply here, and you can see that nice exponential curve as the capacitor charges and it reaches saturation, and then when I press the button, it completely discharges. And of course, we can do that anywhere along the path. And what are you seeing there? That's right. That's the sawtooth wave pattern that we've come to know from capacitors charging. Now, if we drain it slowly, you see that come off just like that. As we slowly charge and discharge, that sawtooth pattern becomes more of a triangular pattern. So that's kind of a little investigation into this. You can change the value of that resistor, the R in our RC circuit, and slow up or slow down the times. Let me give you an example of that. Okay, what we'll do here is we'll take out this potentiometer and we will put in a different one. Let's go up by a decade, a factor of 10. So 1K, here's a 10K. We'll plug that guy in here, maybe, if we get lucky. We'll discharge. Okay, now we're getting somewhere. Let's go up to the scope, and you can see that now. I'm going to adjust that rate here a little bit so it doesn't take all day. Come on. Now it doesn't want to play nice. Figures. There we go. Now I've slowed that down significantly so we can see it climb at a much slower rate. And then by adjusting it, I'll drain it first. You can see how we can adjust. There we go. And make it change speeds. Gotta love that. There's our sawtooth again. But that's a very visual representation of the charging and discharging of the capacitor. Now let's talk more about the math behind it. Okay, we know from Ohm's Law that we can figure out the current at any point in time by finding the voltage at that point in time over the resistance. So as the current charges up the capacitor, VC, which is the voltage at the capacitor, rises across the resistor. So what we get here now is V0 minus VC, and this reduces the current flowing through it. The capacitor continues to charge, but not as quickly. Eventually, VC reaches a supply voltage, which in this case is 3 volts, and the voltage drop across the resistor and the current falls to 0. The capacitor is now fully charged. Without the switch in there, the capacitor would in theory remain fully charged, but you know, there's leakage, there's everything else going on, so it's not really going to behave that way. Now, let's see if we can draw a little graph to explain this. So here's our standard graph. We have voltage in the vertical axis, time in the horizontal axis, and this is the charging of our capacitor. Now, in this state, we'll call this the small resistor, okay? If we were to put in a larger resistor, then it would take much longer for that capacitor to charge. We still have the curve, but the time is much greater. You see, we're reaching our saturation voltage at, we'll call it TX. And with the larger resistor, we're not reaching it until TX plus X, whatever we want to call it. So that is how it works for our charging. Very cool, right? Thing to keep in mind is that the capacitor charge time is theoretically infinite. It never reaches a complete full charge because everything gets cut in half, and, calculus reasons. So now our discharge looks something like this. So here we are at the fully charged point, and then here we are at the discharge point, and this is called exponential delay, and it's often referenced by the small e. So there are a lot of different constants and different values that can be figured out there, but you get the idea. I just think it's kind of cool to play around with different values and charge and discharge capacitors, because as a nerd, as we have already determined, I am quite the nerd. I think it's pretty. And it's 2 o'clock in the morning, so I might be out of my mind. Anyway, that's it for this video. I hope you enjoyed it. If you did, give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. And hey, the winner of the Aneng Q1 multimeter from the patrons is, drumroll please, Mike Oliver. Mike, email me your information. We'll get that meter in the mail to you, sir. That's it. I'm out. Peace.